Today we begin Unit 2 with a lesson about inductive reasoning. Our vocabulary for today: inductive reasoning. This is the use of pattern identification and application to make a prediction. A conjecture is a conclusion based on inductive reasoning. It is unproven and based only on observation. A counterexample is a specific case used to prove a conjecture is false. We're going to start by looking at some patterns here. It would be a good idea to pause the video while you look at numbers 1 through 4 and see if you can extend the patterns. Go ahead and pause and try them out. Hopefully you tried the patterns out and were able to extend them. Let's peek at one that I worked in another class period and see what we came up with. So the first one here, it was all fractions except for the first number, so it's a good idea to put that first number, which was 1, and make it into a fraction so that you're then looking at only fractions. Well, 1 is written as 1 over 1. Each of the numerators were just the number 1, so we're going to continue that. And the denominators in each term were increasing perfect squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on. So you're just increasing the pattern or continuing the pattern by typing in your number you want to square and put that on the bottom. Question number 2. Again, you had that 1 out front, make that a fraction, 1 over 1. And these all had a numerator of 1, so we're going to continue that. And the denominator here is the perfect cubes. So we've got 1 cubed as 1, 2 cubed as 8, 3 cubed as 27. So to extend, we're going to do 4 cubed, 5 cubed, and 6 cubed. Number 3 is one that people often struggle to figure out what pattern is going on there. These are the first letter of the words for counting numbers: 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and it's just the first letter. Number 4 is the first letter of the days of the week. So continuing that, we already have Sunday, Monday, Tuesday, Wednesday, Thursday. Continuing that, we would put F for Friday and S for Saturday. So with patterns, we could do a million patterns together, and there could still be a pattern that comes up that you don't know how to do and how to extend. The more you practice with patterns, the better off you'll be. Some strategies would be to, if there's fractions involved, maybe convert all of the terms into fraction form and then look at it that way so that you can analyze, what is happening between each term. We will not give you ones that are sort of letters based off of, I know that the homework has a question about presidents on it. Google that so that you can answer that. But as far as the quiz and the test go, you won't have to answer questions about presidents or states or anything like that. So the ones that we often ask about are either numeric, or they involve shapes, or the letters would be things more like like the days of the week or the months and things like that. Now, in honors class, we like to use patterns to analyze powers. So we're going to be looking at something a little bit strange for the rest of the notes here. We're going to be looking at patterns when you take a digit and you raise it to different powers. So this first sample question we're trying to figure out is the last digit of 2 to the 81st power. Well, 2 to the 81st power, if you type that in the calculator, the number is too large and the calculator will not give you the result for you to have the answer. So you have to use patterns to get to the answer. What is interesting about numbers like 2, when we raise them to different powers, we're going to see a pattern. And I'm going to use Desmos here to do this, although if I was using a graphing calculator, I would push the y equals button and I would type in the equation that we're about to type in here, and then I would go to the table. I'm going to use Desmos to create a table for me, and I'm going to have it be the equation y equals 2 to the power of x. Now, I don't necessarily want to look at the graph of this. I want to look at it as a table. So I'm going to push this little gear here, and I'm going to pick table. And so it creates a table, and it usually does the -2 to +2, which is a standard table. But for this process, we're looking at a pattern. We want to start by looking at the row where the x is 1. That refers to the first part of the pattern, the first term. And we want to go from there. So I'm going to go in here into the table, and I'm just going to continue the pattern. Okay, so I just sort of extended the table. We are only, again, looking at starting at 1. Because our pattern, we have the first term, second term. We don't have a 0 or any negative terms. So the first part of the pattern, which would be 2 to the 1, is 2. And we have that on our page here. We have the pattern started. So the first one ends in a 2. If the power is 2, it ends in a 4. If the power is 3, it ends in an 8. If the power is 4, it ends in a 6. If the power is 5, it ends in a 2. Notice looking at the last digit here, 2, 4, 8, 6, 2, 4, 8, 6. And we could continue going, and it's going to keep going, 2, 4, 8, 6. So that pattern is continuing in that 2, 4, 8, 6, 2, 4, 8, 6. Now, if we want to know where it's landing for the 81st, we can look at the pattern, and we could count to 81, which would take too long, so we don't really want to do this way, but we could start at that first row and go like 1, 2, 3, 4, and then you want to stop when it's repeating and go back to the top. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And you can count all the way to 81, and whichever one you land on, that's the last digit. Now that would take some time. That's like the backup emergency plan. The process in this is to first take your base, your 2, raise it to the power of x, and look at the table. Locate the pattern that's happening by starting with x value of 1, and then write the pattern until it repeats. The first repeat here was when it had a 2 at the end of 2 to the 5th. So you want to ditch that. You want to look at how many are in the sequence. There are 4 in the sequence. You want to take your power, your 81, and you want to divide it by 4, because this will tell me how many times I've made it through in my counting. As we were putting those dots, it will tell me how many times I cycled through all 4. Now, with this kind of division, we do not want a decimal. We want to do kind of old school, elementary school division. You want to look for the remainder. The remainder is going to tell me where my answer is. So looking at 4 dividing into 80, well, 20 would be the closest. And when we divide 81 by 4, giving us 20. 20 times 4 is 80. Subtracting 80 is a remainder of 1. So that remainder of 1 is what you want to think about. If you have a remainder of 1, you are going to be in the row 1 of the pattern. Remainder of 2, you are in the second row. Remainder of 3, third row. Now, you are dividing by 4. You will not have a remainder of 4. So the last row would be when it divides perfectly. If it divided perfectly, we would end on that last row. We would have nothing left over. And so this last row is when there is no remainder. So we divided and we had a remainder of 1, and that puts us at row 1, meaning we had 1 left over as we were cycling through, which says we are having that 1 at the top that we would get to when we counted and ended at 81. So 2 is actually the answer to the question, because the remainder was 1, which means go look at row 1. The last digit for row 1 is 2, so 2 is the answer. It's kind of weird. It definitely takes some getting used to. It's really, really cool, though, that the digits, when they are raised to powers, do create patterns. And so we're going to look at some more numbers and see what happens with them. So this next one wanted us to look at the last digit of 3 to the 38. So I'm going to go in here, and I'm just going to change this 2, and I'm going to make it a 3. And again, remember, we are starting at this where it says 1. So we want to think of the pattern as we are looking at 3 to the 38. You want to think about how 3 to the 1 is 3. Always be sure you start with the power of 1. People forget to start there, and then that will mess everything up. 3 squared is 9. 3 cubed is 27. 3 to the 4th power is 81. 3 to the 5th power is 243. So as you're looking at this table over here on the right of my screen, the first row where the 1 is at, be sure you're starting there. 3, 9, 7, 1, 3, 9, 7, 1, 3, 9, 7, 1. You can see that it is repeating those 4 values. So once it repeats that 3 at the end, you want to ditch that 1. You want to only look at the pattern before it's repeating to see how many are in the pattern. There are 4 in the pattern, just like last time, but it is not always 4 in the pattern. And so the power was 38. So you want to take that power of 38 and you want to divide by 4. And you want to look for the remainder. Well, 4 going into 38, it's between 9 and 10, because 4 times 9 is 36, 4 times 10 is 40. So we have to round down, we have to go with the 9, which gives me 36, and subtracting that's 2. That is a remainder of 2. What this tells me is that my remainder of 2 will land me on row 2 for the answer that I'm going to have. So 9 is the answer to this question, because 9 is on row 2, and remainder of 2 tells me to go look at row 2, and then that is the last digit. Of course, you could count to 38. That wouldn't be too bad. Just be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And just see where you land at 38. And that's the backup plan if you are struggling to do the alternate method that I am showing you here. Now, we always divide by 4. The answer to that is no. Here they're asking about, what happens if it's 6 or 5. If we replace this with a 6, you can see that, again, start at just the 1 here. 6 is the end of every row. So 6 to any power ends in a 6. And if I replace the 6 with a 5, you can see, again, start on 1 here. Don't go above there because that doesn't make sense for the pattern, but they all end in 5s. So the 5 to any power is 5. Other numbers that are like this would be, let's see, trying to remember which one does this. 9s have 2 in them. So which numbers have 2 places? 9 had 2 places. Right now I'm just kind of guessing and checking. We looked at 6, we looked at 5. Let's look at 7. 7 has, starting here, 7, 9, 3, 1. 7 has 4 in the sequence. Let's look at 8. 8, 4, 3, 2. 8, 4, 2, 6. 8, 4. So 8 has 4 numbers in the cycle. We looked at 9. We did not look. We looked at 2 and 3. Let's look at 4. 4, starting at 1 here. 4, 6, 4, 6. 4 has 2 digits in the sequence. So we looked at 2, we looked at 3, we looked at 4, 5, and 6. We looked at 7, we looked at 8, we looked at 9. Let's look at 10. If you look at the 10s starting at the 1, they all end in 0. So 10, it works out like the 6s and 5s where they all end in the same number. And 11, I believe, also does. Yeah, when we look at starting at 1, they all end in 1s. So 11 also has that happening. So these are some patterns that you will want to practice and make sure you're able to do them. I told first period a set of problems to try out, so I'll put those on the screen. I told them to try these for sample problems to see how they are able to work out those questions and find the right answers. So these would be a good set to try and see if you can find out what the last digit will be. Again, this video I used Desmos, but in class, if it's a quiz or a test, we have to use our graphing calculator, so make sure you know how to get a table out of the graphing calculator to help you with these. And let me know if you have any questions.